Greetings. First and foremost, let me remind you that you can enable automatic captions in English and then use the translation feature to view them in the language you're most comfortable with. Welcome back to the fascinating world of positional numeral systems. In our previous lessons, we explored why the base 10 system was chosen for the Indo-Arabic positional numeral system. Do you remember the answer? Precisely. It's because we humans have 10 fingers, making base 10 a natural and comfortable choice for us. Now, let's delve deeper into this concept. Imagine, for a moment, that instead of being the advanced, upright primates we are today, we were an equally advanced version of a three-toed sloth. This particular variety of sloth has 3 fingers. 6 in total. Imagine, then, that the most intelligent life form on Earth was not humanity but a highly evolved species of sloth. In such a case, what do you think their numeral system would look like? For simplicity, let's assume they would choose base 6. Using the same principles of positional notation, let us now explore what a base 6 numeral system might be like. So, I invite you to join me as we take another step along this journey, deepening our understanding of numeral systems and the wonders they hold. To understand how positional notation works in base 6, let's draw an analogy with base 10. In base 10, objects are grouped in sets of 10. This grouping defines the 10 unique symbols, or digits, of the Indo-Arabic numeral system. There are 9 digits, from 1 to 9, and an additional symbol, the 0. Together, these form the 10 symbols of base 10. Now, let's think about base 6. Here, we use only 6 symbols: 0, 1, 2, 3, 4, and 5. But what happens after 5? Instead of introducing a new symbol, we group 6 objects together into one unit and create a new place to the left, where each unit represents 6. This means that the number 6, as we know it in base 10, is represented in base 6 as the digits 1 and 0. To make this concept clearer, let's revisit an old friend, the abacus. On a base 10 abacus, each column has 9 beads. But how many beads would there be in a column of a base 6 abacus? That's correct. 5 beads per column. Let's imagine a base 6 abacus with 3 columns. The rightmost column represents single units. The middle column represents groups of 6 units. And the leftmost column represents 6 groups of 6, 36 units per bead. Let's begin counting. Starting from 0, 0, 1, 2, 3, 4, 5. Now we've reached the maximum number of beads in the rightmost column. What happens next? We reset the column to 0, add a bead to the next column, and represent this as 1, 0 in base 6, equivalent to 6 in base 10. Continuing from there, 0, 1, 1, which represents 6 plus 1, or 7 in base 10. Next, we have 8, 9, 10, and 11. The next number is 0, 2, 0, which is equivalent to 12 in base 10. The pattern continues, and the largest two-digit number in base 6 is 0, 5, 5, which equals 35 in base 10. What comes next? It's 1, 0, 0, representing 36 in base 10. Now, let's practice converting numbers between bases. Consider the base 6 number 423. What does this represent in base 10? To answer, we follow the same principles as in base 10 arithmetic. The leftmost digit is multiplied by 6 squared, the next by 6 to the power of 1, and the final digit is added as is. That is, 4 times 36, plus 2 times 6, plus 3. This equals 144, plus 12, plus 3, which sums to 159 in base 10. Let's adopt a convention to clarify the base of the numbers we're working with. From now on, we'll write base 6 numbers with a notation like 4, 2, 3, in larger letters, and the word 6, in subscript, to indicate the base explicitly. Why write the word 6 instead of using the digit 6? It's because base 6 doesn't include the symbol for 6, and writing it out provides clarity. Now try it yourself. Convert the base 6 number 351 to base 10. Pause the video and give it a go. Here is the solution to the exercise. Now, let's move on to an exercise to perform a conversion from base 10 to base 6. Now, let us discuss converting a number from base 10 to base 6. The number 91 is in base 10 because, in our convention, when the base is not explicitly written as a subscript to the right of the number, we assume it to be in base 10. So, how do we convert it to base 6? We will explore two methods. The first is intuitive and easy to grasp but can be laborious to execute. The second is more sophisticated and allows for quicker results. Let us begin with the first method. Here, to the right of the equals sign, we will place the positions where the digits of the number in base 6 will appear. Do you recall the value of the rightmost digit in such a positional system? Exactly. In this position, each unit is worth 1. Thus, the digit 3 in this position would indeed represent 3 units. Now, what about the second position? Here, each digit is multiplied by 6. Therefore, the digit 2 in this position represents 12 units. And the third position, what does each digit represent there? Correct. Each digit here represents 6 times 6, or 36 units. What if there were yet another digit to the left of this one? Indeed, that digit would represent 6 times 36, or 216 units for 1 in that position. Now, let's proceed with the conversion. In this more intuitive method, we begin by determining the largest digit for the leftmost position that fits within the number. Let us investigate. In this position, the number 3 corresponds to 108. Far too large. But 2 corresponds to 72 units, which fits. At this stage, we have the partial number 2, 0, 0 in base 6, equivalent to 72 in base 10. The difference between 91 and 72 is 19. So we continue to the next digit. Now, consider the second position. In this position, 1 corresponds to 6 units, 2 corresponds to 12, and 3 to 18. 4 would correspond to 24, but that exceeds the 19 we are working with. So, the second digit is 3. Converting this partial result to base 10, we calculate 2 times 36 plus 3 times 6, which gives us 90. Now, we need to complete 91. How much is missing? Just 1. To finish, the final digit will be 1. Thus, the resulting number is 2, 3, 1, in base 6. Now that you've understood this method, let's practice it once more with the following exercise. Consider the number 51 in base 10. Convert it to base 6 using the intuitive method we've just explained. Pause the video now, complete the exercise, and then resume to check your answer. So, how did it go? Did you manage to complete it? Here's the answer. Check your work. If you made a mistake, take a moment to try again. If you got it right, let's move on. You've likely noticed that this method is both simple and intuitive. However, you may have also observed that it can be quite tedious and time-consuming. And indeed, it is. This method, while effective, is rarely used in practice because of its labor-intensive nature. The method most commonly used in practice is the method of successive divisions. It is remarkably simple and efficient. The user begins with a number in base 10. Let us revisit an example we just explored, converting the number 51 from base 10 to base 6. To begin, the user takes the number 51 in base 10. The process is straightforward. Divide 51 by 6, and record both the quotient and the remainder. Next, take the quotient and divide it again by 6, noting the new quotient and remainder. This sequence continues, dividing by 6 and recording the results, until the quotient becomes less than the divisor, in this case, 6. At this final stage, the user collects the sequence of results. The first digit of the new number is the last quotient obtained. Following this, the remainders are noted, but in reverse order, from the last remainder to the first. And, as if by magic, the number 51, written in base 6, emerges as the result. You may have noticed that this method is significantly faster and more practical than the previous one. But perhaps you're wondering, why does this method work? In our next lesson, we will delve deeper into the reasoning behind this technique. We'll also begin exploring other fascinating discussions related to this topic. So, I look forward to seeing you in the next lesson as we continue this exciting journey of discovery. Best wishes and see you there.